Welcome to Part 3 of Module 9. The learning outcomes for the third part of Module 9 are: perform calculations related to the different equilibrium constants, and calculate the percentage ionization of weak acids. We will now cover some calculations, so it is a good idea to have your calculator handy to practice during the lecture. In this section, we will look at the concept of equilibrium and do some relevant calculations. For this chemical equilibrium equation, the capital letters represent the reactants and products. The lowercase letters are the stoichiometric coefficients. The equilibrium constant is referred to as KEQ, and it is equal to the formula shown. The molar concentration of products to the power of the stoichiometric coefficients divided by the molar concentration of the reactants to the power of the stoichiometric coefficients. Only substances that have molar concentrations are considered in this expression. We exclude solids and solvents from the equilibrium constant expression and generally only include aqueous solutions and gases. Let's have a look at the following equilibrium equation. 3H2 plus N2 gives 2NH3. The equilibrium expression is written as the molar concentration of the product ammonia to the power of 2 divided by the molar concentration of nitrogen gas and the molar concentration of the hydrogen gas to the power of 3. If we know the molar concentrations of these substances, then we can calculate the equilibrium constant. The magnitude of KEQ can tell us where the equilibrium lays, whether it lays heavily to the right side in favor of the products or towards the left side in favor of the reactants. A large value for KEQ, around 100, means that the equilibrium is in favor of the products. For example, if the product concentration in a chemical equilibrium is around 1 molar and the reactant concentration around 0.005 molar, then the KEQ will equal 200. On the contrary, a very small value for KEQ, around 0.01, means that the equilibrium is in favor of the reactants. For example, if the product concentration in a chemical equilibrium is around 0.005 molar and the reactant concentration around 1 molar, then the KEQ will equal 0.005. KEQ values around 1 means the equilibrium is shared between the products and the reactants. Let's practice some examples. Calculate the value of KEQ for the following equilibrium, where the concentration of hydrogen gas is equal to 0.228 molar, I2 concentration is 0.228 molar, and HI concentration is equal to 1.544 molar. The equilibrium is H2 plus I2 gives 2HI. Pause the video and practice using your calculator to solve this question. The answer will be revealed after you continue. As we have the molar concentrations, then we can use the equilibrium constant expression and plug in the numbers. KEQ equals 1.544 to the power of 2 over 0.228 times 0.228 will give 45.9. So the answer is E. Remember that a large KEQ means that the relative amount of products compared to the reactants are favoured. As we mentioned in Module 8, water undergoes auto-ionization, as shown in the following equation. H2O plus H2O gives H3O plus OH minus. In pure water, the concentration of hydronium ions is equal to the concentration of hydroxide ions, and that is at 1 times 10 to the negative 7 molar. From that, we can determine a new constant called the ion product constant for water. So the Kw, the W stands for water, is equal to the concentration of hydronium ions times the concentration of hydroxide ions, and is equal to 1 times 10 to the negative 14. This constant is calculated at 25 degrees Celsius. So in any aqueous solution, you will find both hydronium and hydroxide ions. If you know the concentration of one ion, you can calculate the concentration of the other ion using Kw. We learnt from the previous module that the pH is equal to the negative log of the concentration of hydronium ions. The P refers to the negative log, and it can be used with different variables. For instance, pOH is equal to the negative log of hydroxide ion concentration. So if we take the logarithm of the first equation, we can say that pH plus pOH is equal to 14. From this table, you can see that the Kw is always 10 to the minus 14. The other four variables, namely the proton and hydroxide ion concentrations, and pH and pOH, can change according to the solution. So if you are given any one of these variables, you should be able to calculate the other three variables. Let's practice some examples. Calculate the concentration of hydrogen ions in a 0.0152 molar NaOH solution. Sodium hydroxide is a strong base, and as we saw previously in Module 8, it will completely dissociate in water. So if we have 1 molar of sodium hydroxide, we'll get 1 molar of hydroxide ions and 1 molar of sodium ions. We have a 0.0152 molar solution, so the concentration of hydroxide ions is also 0.0152 molar. By rearranging the equation, concentration of H plus times concentration of OH minus equals 1 times 10 to the negative 14, we can calculate the concentration of hydrogen ions is equal to 10 to the minus 14 over OH minus. Thus, the concentration of H plus is equal to 6.58 times 10 to the minus 13 molar. Now we can calculate the pH of the solution. The pH is equal to 12.182, which makes sense as we have a strong base, so we would expect the pH to be above 7. Another approach we can use to solve this question is by calculating the pOH, which is equal to 1.818. And then from the formula pH plus pOH is equal to 14, we can calculate the pH as 12.182. What is the OH concentration in a 0.0001 molar solution of HCl? The answer is B. HCl is a strong acid, so hydrogen ion concentration is the same as that of the acid at 10 to the minus 4 molar. Thus, the concentration of OH minus is 10 to the negative 10 molar. Now we will investigate weak acids. Remember from Module 8 that weak acids don't completely ionize, and they remain in equilibrium. The acid ionization constant, or Ka, for a weak acid is a measure of the extent to which the acid ionizes in water. Water is the solvent, and its concentration doesn't measurably change during ionization, so it does not go into the Ka expression. For example, acetic acid partially dissociates into acetate ions and hydronium ions. The equilibrium constant for weak acids is called the Ka, with the A standing for acid. It is expressed by the formula shown. There is no power in any concentration, as the stoichiometric coefficient is 1 for all the substances. As you can see, the value for this acid is 1.8 times 10 to the negative 5. This very small value indicates that the equilibrium lays more heavily towards the left and favours the reactants. For every weak acid, there is a constant Ka that tells us how much of the acid dissociated. You don't need to memorize these values. This table gives some examples of different Ka values for different weak acids. Using the table, rank the following acids from strongest 1 to the weakest 5. For this question, an acid with a high Ka value will be stronger than an acid with a low Ka value. Hydrofluoric acid is the strongest amongst these acids, as it has a Ka of 6.5 times 10 to the negative 4. Nitrous acid comes next with a Ka value of 4.5 times 10 to the negative 4. The weakest acid in this example is acetic acid with a Ka value of 1.8 times 10 to the negative 5. Determine the hydrogen ion concentration, pH, and percent ionization of a 0.2 molar solution of acetic acid with the Ka shown. Acetic acid is a weak acid, and the following approach needs to be used when solving questions for weak acids. First, we set the ICE table, which stands for initial, change, and equilibrium. At the initial point, we have 0.2 molar of the acid, and this amount hasn't changed as the reaction hasn't started yet. We will ignore the original hydronium ion concentration in the solution and assume this to be approximately 0. There is no reaction yet, so no conjugate base has formed, so let this concentration be 0. In the change row, after the reaction has started, let's assume that an X amount has dissociated from the acid. According to this stoichiometry coefficient, X amount should be produced for the hydronium ions and X amount of the conjugate base C2H3O2-. At equilibrium, the concentration of the acid that will be left over is 0.2 minus X, and the concentration of the products will be X. We can write the equilibrium constant expression as Ka equals the concentrations of H3O plus times C2H3O2- over HC2H3O2. The Ka value of acetic acid is 1.8 times 10 to the negative 5. We need to solve for X. If you want, you can rearrange the equation and you will notice it has the form of a quadratic equation. However, for the purpose of this course, you don't need to do that. Because X is expected to be very small, we can simplify the expression to avoid dealing with quadratic equations and ignore this amount. The simplified format looks like Ka equals 1.8 times 10 to the negative 5, which is equal to x squared over 0.2. Let's rearrange the equation to solve for x. X squared equals 1.8 times 10 to the negative 5 times 0.2, which is equal to 3.6 times 10 to the negative 6. So, to calculate x, we take the square root of 3.6 times 10 to the negative 6, which will give us 1.9 times 10 to the negative 3 molar. Remember that x is the concentration of the hydronium ions, so pH is equal to the negative log of the hydroxide ion concentration, so the negative log of 1.9 times 10 to the negative 3 is 2.72. So the pH of the solution is 2.72. The question also asked us to calculate the percent ionization. To do that, we divide the concentration of the hydrogen ions over the initial concentration of the acid times 100%. The concentrations are as in the table. So we put in the numbers and the answer will be 0.95%. So less than 1% of the acid dissociated. Let's look at another example. Hydrocyanic acid, or HCN, is a weak acid whose Ka value is 4 times 10 to the negative 10. What is the concentration of hydroxide ions in 0.1 molar HCN? The answer is B. HCN is a weak acid, and we can use the ICE table to calculate X. Remember that we use the simplified format of the expression to avoid the quadratic equation. Because the amount of X is very small, we can consider that the concentration of the HCN remained the same as per the table. This is the end of Part 3 of Module 9. Please proceed to Part 4 that will cover the acid-base properties of salts and the buffer solutions.